So the biggest thing we're going to talk about this week is valence electrons, and something we started out talking about yesterday in class. There is a pattern of valence electron counts across the table, and it's all has to do with the S and P sublevel block elements. So that is the elements that are in this group here, or in these two groups here, and then in this section over here. Now, the transition metals, for the most part, and the intertransition metals do not have a definite count of electrons in their outermost shell, energy shell. The rest of the elements do. So the pattern is that group 1 has 1 valence electron, group 2 has 2 valence electrons. The valence electron count within these groups varies. So we skip over here. So it's 1, 2. We skip over here to group 13. This has 3 valence electrons. Group 14 has 4. Group 15 has 5. Group 16 has 6. Group 17 has 7 valence electrons, and group 18 has 8 valence electrons. Now, the exception is helium. Helium only has 1 energy level because, as you should recall, helium and hydrogen only have 1 energy shell. So speaking of that, don't forget that the period numbers are like energy shells. They are the number of energy levels that particular element has. So I could choose any given element on the table. Say silicon, for example. Silicon has 3 energy shells, so its outermost energy level is energy level 3, and it has 4 valence electrons. Now, there are ways that we can describe or represent these valence electrons, that is, and that is something that we're going to practice with and go over. Now, first of all, group 14, that is carbon, silicon, germanium, all of these right here have 4 valence electrons, all right? Now, we can verify that in a number of ways, all right? So first of all, something that we worked on last semester was electron configuration. 1s2, 2s2, 2p6, 3s2, 3p2. This is the electron configuration for silicon and no other element. Silicon has 14 total electrons, not valence electrons, but total. That's because its atomic number is 14, okay? So we go through the 1s, then the 2s, then we go through 2p, 6, 3s2, 3p2, and that puts us on silicon. So the last set of the last set of quantum numbers is 3p2. Silicon is the 3p2 element on the periodic table. Now, going back to this whole valence electron count thing, please realize that the outermost energy level for silicon is energy level 3. And you can even see that when we go over here and see that silicon is in period 3 on the table, okay? Now, when we look at the electrons, that totals up to, in energy level 3, we have 4 total electrons. These are known as the valence electrons, VE. So, electron configuration is a way to confirm the valence electron count within the total count of electrons that's in the electron configuration. So you can identify them that way. So here's my valence electrons. That's a total of 4. Now, another way we can do this is by drawing, and we've already confirmed it because it's in group 14, so that's 4 valence electrons. Another way is by drawing out a Bohr model. Now, remember that Bohr didn't know anything about the S, P, D, F. He didn't know anything about sublevels. He just knew about these. He knew about the principal energy levels. Energy level 1, he knew about these rings. Energy level 2, he thought that the electrons were in these simple energy levels or rings, these orbits surrounding the nucleus. Now, what we need to always remember is that energy level 1 stops with 2 electrons in it. That's it. It fills up with 2. Every other shell will become stable or full with 8, because something I mentioned yesterday and I want to reinforce today is that the S and P sublevels are the most important, okay? So they are what dictates chemical stability as long as they are filled up in that last valence, okay, shell. So let's take a look at that, at a Bohr model, that is, for silicon. So we're going to draw out, we're going to say silicon, this is in silicon's nucleus. Silicon has how many protons and electrons total? Well, it is atomic number 14, so it has 14 protons in the nucleus. It's got 14 total electrons in its electron cloud, okay? So we're going to show this, okay, as we draw out the Bohr model. So energy level 1, we've got energy level 2, energy level 3. At this point, some students are like, how did you know to draw 3 rings? Well, it is in period 3 right here, okay? So going back over here, we are in period 3, which is basically the representative number of energy shells for an element. So that's why. And we can see right here, we're going to go out to energy level 3. This is where the electron configuration stops. So there's many ways to verify this. Now, I just like to draw electrons as dashes that look like negative symbols. All right, so silicon has 1, 2. Now notice that I don't put the electrons next to each other because I just have them spread out in this energy shell. Now, when I start doing the others, you're going to see that I spread them out in 4 different sections, and this is standard for doing a Bohr model. This may not be the way you learned it in physical science or in previous science class, but this is how we construct Bohr models in chemistry, because we've learned a little bit about orbitals and electrons pairing up in them and that sort of thing. So, in the second energy shell, 1, 2, 3, 4, 5, 6, 7, 8. Notice that I spread them out before pairing them up. Now you can draw dots for the electrons, but to me that's so much more time consuming. So far we've drawn 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. And then this is going to be 11, 12, 13, 14. Notice that I spread them out before I pair them up. I'm still kind of applying that Hund's rule thing within the Bohr model, okay? So here we have 14 total electrons, and here you can see are those 1, 2, 3, 4 valence electrons. So we are once again confirming that silicon has 4 valence electrons, all right? 4 valence electrons. We can see the 4 valence electrons here in energy level 3. We can see them here, okay? Now, lastly, the way that we can represent our valence electrons is by drawing a Lewis structure, which you guys have a periodic table that displays these. But silicon, when you draw a Lewis dot structure, you're only drawing or including the valence electrons, those outermost chemically dictating properties, those electrons within the electron cloud. So silicon has a total of 4 valence electrons, so we draw these as dots. So we're not going to draw these as dashes around silicon. My pen is not wanting to work. Okay. Okay, I know those are really ugly dots. My pen's acting funny. All right, so notice that I spread them out, and just like if I was going to have another element, say like I was going to have chlorine. Chlorine has 7 valence electrons. I would do this same sort of thing where I'm spreading them out before pairing them up, and it doesn't matter what I spread them out to. I'm going to get it in a second. All right. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. All right. Okay, there we go. So you can see that chlorine has 1 more that would make it chemically stable, so it's got 7 valence electrons. All right. Now, just to show you that you do spread them out before you pair them up. I apologize for my pen, my Apple pen being silly. All right, now, one of the things we also want to talk about is like chemical stability. We're going to do this by looking at another element, so I'm going to clear off the screen. All right, so other than valence electrons, you guys will have to learn and know what oxidation numbers are. Oxidation numbers are the charges that an element will inherit once it becomes chemically stable. So do recall that the noble gases are completely chemically stable. So I'm going to just draw this yellow line through, highlighted line through it, just to say that, just to represent that these right here are not going to chemically bond with anything. So the thing is that all the rest of these elements on the table want to be like these guys. They want to be noble gases. They want to be chemically stable and have that full outer energy shell. So basically, as long as you fill up your S and your P sublevels, that allows you to be a noble gas. It allows you to be chemically stable with a total of 8 valence electrons. So stability comes when an element has a full valence shell. Now, there are one of 3 ways that an element can become chemically stable. It can lose, gain, or share valence electrons, okay? Now, so I'm going to pick on an element, okay, just to demonstrate this, a couple of different elements to demonstrate this, okay? Now, so we learned that there is a valence electron count, 1, 2, that goes across the table, 3, 4. I'm not going to draw the VE over here because we saw last time that it gets kind of crunched up, okay? But this is the valence electron count across the periodic table. Again, these 3 right here, as y'all saw on your periodic table with the Lewis structures, they also have set valence electrons as well. Silver always has 1, zinc always has 2, and cadmium always has 2. All right, so these are our valence electron counts. So if I'm going to sit here and look at, say, oxygen, oxygen has 6 valence electrons. My Apple Pen does not like doing Lewis structures, and I am mad at it because of it. It's okay. Okay, so new plan, okay? So basically, oxygen has 6 valence electrons, which means in order to be chemically stable, it needs 2 more valence electrons, okay? Well, here's what happens when that occurs. So when oxygen chemically bonds with another atom, it will actually, oxygen, this is the Bohr model for oxygen, okay? Look at that, I can do the dashes. Okay, so that's a total of 1, 2, 3, 4, 5, 6, 7, 8 total electrons that oxygen has. And then 6, you can see here are the 6 valence electrons, okay? Now, in order to become chemically stable, oxygen needs 2 more electrons to come in and fill up that valence shell. So it has to get that by bonding with another element. Now, when this happens, oxygen will get a charge, okay? This will make oxygen have a 2 negative charge. And everybody's like, what does it mean? What? Okay, well, let's go back. If we think about oxygen, oxygen has 8 protons, because that's its atomic number. You can see oxygen is atomic number 8. It's got 8 protons and it's got 8 electrons. Every atom is born, so to speak, in the free state with equal proton and electron counts, okay? Now, when it goes to bonding right here and it takes in electrons for chemical stability, well, that makes it charged. Now, when oxygen chemically bonds, okay, so let's just say this is still oxygen, okay, it's still got 8 protons in its nucleus, but now it's chemically stable with a full shell, okay, it now has a negative charge, okay, because it now still has 8 protons, because that's what makes it oxygen, but it now has 10 total electrons, which means we have an abundance of electrons by 2. So this makes it have a charge of 2 negative. This is what is known as the Ionic Charge, okay? It's also known as an oxidation number, okay? So that's what that 2 negative is. Now, the thing is all elements in this group, right here have what is known as a 2 negative ionic charge, okay? So these are my valence electrons, okay? But what I'm introducing to you now is the charge that an element will acquire once it gains valence electrons or loses. Now, it can lose them as well. So we're going to talk about how an element like beryllium or magnesium will actually lose its valence electrons, okay? And so we're going to talk today in class about what is known as an ionic charge or an oxidation number, and how it develops, and how there is a pattern across the periodic table, how it develops from an element becoming chemically stable. Now, do realize that once oxygen gained those 2 valence electrons, that means that oxygen has a new electron configuration that looks like neons. Okay, but that's what all elements are going to do. Like, so once oxygen, this is oxygen as an ion, this is its electron configuration. Normal oxygen looks like this: 1s2, 2s2, 2p4. But once an element chemically bonds and either loses or gains or shares electrons, it gets a new electron configuration known as its ionic electron configuration. So we're talking about how once elements become charged and lose or gain electrons, they become ionic. They become ions. And we will pick up on that this week and today.